cold this morning, huh?
Yeah. Sure. Has Samuel the physics puzzle today?
Yeah, what time today?
I'm not sure.
Yeah. When I go home, that's it. Today is a special day. It's my 10-year marriage anniversary today.
You got married?
Yeah, 10 years ago today. Yeah, so when I go home, I'm not going to be thinking, better check Lee's physics coursework. I'm going to be thinking, I better bring a present home or I'll be in trouble.
Okay.
So if you send me something, it needs to be before I go home today.
When did you go home?
I think I'll leave at about 4 o'clock today.
Okay. Should you have a back?
No. After teaching students, I decided I don't want kids because kids are smelly and stupid. Okay. We're continuing now. We're going to have a look at something called Hooke's Law, which some of you might already know. You know Hooke's Law. It's good. Would you know it well enough to give me the definition? Not just springs, but springs essentially. Do you know? It doesn't sound like you do. Okay, Hooke's Law. Oh, Chew, you drink those drinks? They're so bad for you.
Why?
Those energy drinks?
Yeah.
Oh,
Why
makes me
is
sad.
that? My roommate drinking all day.
All day?
I need more.
Well, I don't know. You're drinking a Sprite, so. Hooke's Law, you got that? Hooke's Law? Okay. So, here's the concept. The more you pull this, the more it pulls back. So what happens when you pull it more? You get more of a force trying to pull it back. This actually is basically Hooke's Law. Hooke noticed that as you extend the spring, there's more of a force acting back. A restoring force. So Hooke noticed, and this is his law, that the force F that you need to extend or compress a spring by a distance x is proportional to that distance. Totally off. Okay. What is that as a formula? So as a formula, well, do you know what it is, Monica? Yeah, that's one way to state it, yeah. I use the x, or sometimes delta x. So the force is equal to minus k delta x. Now, the reason for the minus is to indicate that the force acts in the opposite direction. So if you double the extension of the spring, you double the force the spring requires to extend. This makes sense. You know, as you pull something apart, you need more and more force as you stretch it. It gets harder and harder to pull. Are you happy enough with that? Where K, as you said, Monica, is a constant. Different for each material. It's a feature of the spring. It's different for each material. It's also called the stiffness constant. And X is usually a small number, you know, a few centimeters or millimeters, compared to the total deformation of the spring. So basically the x compared to the length of the spring is quite small. So you have a spring and you extend it a little bit, usually. What's the units for K? Newton per meter is the units for K. Can you see that? Yeah, Newton per meter. So basically it's like saying if the K is 2 newtons per meter, then it's like saying for each meter of extension there's an additional 2 newtons of force. So 1 meter extension is 2 newtons. 2 meters extension is 4 newtons, and so on. So it's kind of a simple formula. It's a linear formula. It shows a linear relationship between the force and the extension. Okay, so continuing now with this. So definition of some terms. What do you think the natural length means? Yeah, so what's another word for natural length in this sense then? Original length. The length before you extend, yeah. So the natural length L of a material is the length at which the material wants to return to. So for example here, if I pull this and let go, it will go back to its natural length, the length it's trying to achieve. It's the length before any force is applied, as you said, Monica. That is, it's the length it wants to be at. Now there's a lot here for the exam. I think the first sentence or the second sentence, or maybe even the third sentence by itself would be enough. See, these medicine students, they have these pens which look like medication. This is a pen. Doctors.
Oh, it's pharmacy. Can it go?
This is from a pharmacy student?
Could be.
That's weird. Okay. Yes, next. Yeah, okay. Now, does anybody know this word extension? Want to give me a sentence? Close enough. The extension is the length at which the material is extended beyond its natural length. So in other words, it's just the extra length. That is the x in the formula. No, that's, are you thinking about the letter E? Because some formulas use the letter E instead, and that's why. E for extension. Yeah. Not as clever as that. Yeah? Got all that, dudes? Yeah? Okay. So this will not shock you to discover the graph looks like this. As the extension increases, the force increases as well. No surprise. But what does the slope of this graph represent? Let's have a look at that. So if this is force and this is x, this is 0, 0, and we'll call this point here xf, then the slope of the graph is f minus 0 over x minus 0, which is f over x. But remember, f equals kx, or, well, minus kx, but I won't worry about the minus. The minus is just to tell me that it's going that way if I'm pulling it this way. Anyways, what is f over x? Well, if you look at this formula, f over x is equal to k. So the slope of this graph is equal to the k constant. Yeah?
In the law, when we learned the factors, we had to mention as long as the string levels which is constant.
Now that's, we're getting to, yeah, I haven't introduced that idea yet, which will come up quite shortly. But you're right, there is a limit here to this, yeah. So this is what the graph looks like for small x. Could you draw this and state that the slope is equal to the k? Can you draw this, Chu? Yeah.
Teacher,
Yes.
Sean said he slept in the bus, there's no stop. I don't know where I am. I'm looking for way back.
Oh, Sean. The adventures of Sean. Exactly, yes. Well, what time are we at now? Hang on, let's see. Yes, 9:20. Dun, dun. Maybe we should take bets to see if he can make it back here on time. How lost do we think he is? He's sounding quite lost.
I cannot think of. Maybe he.
Yeah, what bus does he take? How far away could he be?
At some point,
I don't know, but I think.
No, does he? The Lewis. Maybe he's out in Dundrum Shopping Centre now. Okay, did you draw that? Continue? Yeah? Okay. So, we've looked at what the slope is, but let's have a look at what the area is. Okay, so what's the area here? So the area is half the base by the height, which is a half x kx, which is a half x, a k x squared. Yeah? Now, that's fine, we have a formula, but what exactly does that formula represent? Well, to get a little bit of a hint, let's have a look at the units. So if we look at the units here, this will be in units of meters, and this will be in units of newtons. So this will be in units of what? Try again, Monica? Just Newton meters. Which is what, actually? What's a Newton meter? Yes, it's a joule, which represents energy. So in fact, what is happening is an area is the energy. Now, the energy of what? Well, if you can imagine, if you pull the spring out, you have put energy into it, because the moment you let go, what happens? It pulls back, and your energy turns into what type of energy? Kinetic energy. So in essence, you're given the spring potential energy. You're storing energy in it and you release it. So you end up with this formula now. Potential energy is a half kx squared. So this is the energy required to take it from its natural length to x. Now if you don't want that, like maybe the spring is already stretched and you just stretch it more, then it will just be the area of how much you stretched it. So like if it already was here and you pulled it an extra distance, it's just going to be this area, which, you know, all you have to do is get the whole area and minus this piece. We don't usually deal with that in the exam. Usually in the exam what happens is it's at rest and then you pull it from rest. So that formula is when the spring's at rest and you stretch it and release. Yeah? This is more like mechanical energy. It's stored in the mechanics of the machine, like the cogs, the wheels, the springs. Kinetic energy is due to the motion. So when you pull the spring and let go, there is no motion, but there's still energy in it. So that's what we mean by mechanical energy or potential energy. Yeah. When you release it, it becomes kinetic. Yeah? Continue? Yeah? Okay. I didn't actually put these formulas in a box, I don't think, which I should have perhaps. Anyways, this is ideal, meaning in real life it's not quite like this. As Monica was saying earlier, in real life the graph is a bit more like this. That as you extend it, you get more force. But then at some point it breaks. It doesn't stretch anymore. It loses its stretchiness. I don't know if you've ever seen that, but you can imagine it. If you have a spring and you stretch it, but if you stretch it too much, then it loses the ability to return correctly to the original shape. Yeah, it might try to return. It might then go like this, you know, but it won't actually return back to the original here. So if you pull it too far, what will happen is it loses its restoring force, its ability to snap back. And that's why the graph flattens off here. It's no longer as stretchy anymore. This point here is called the elastic limit. The elastic limit. This is reached when the graph line starts to curve. So here, we're good, and now, elastic limit. What's not on this graph, which you need for the exam, because in the exam, I've seen them ask you to make this graph 3 or 4 times. They ask you to make a graph of force against extension. But to get full marks, you need to have 4 things about your graph. Number 1, the shape. So the shape should be like this. Number 2, you need to mark where the elastic limit is. So you put a mark here and say elastic limit. Number 3 and 4 is you have to write the name of this part and this part. Okay? So this part here has a name, and this part of the graph here has a name. Yeah? I'll give you a hint. This part here is called the elastic region, because elastic in English means stretchy. So does anyone want to guess what the second part of the graph is called? Ah, wonderful. It gets students every year without fail. Believe it or not, it's not called inelastic. Not super elastic, not unelastic, not anti-elastic, not aelastic, not over-elastic, not under-elastic, not pre-elastic or post-elastic, not pro or con elastic,
No elastic.
no elastic, not non-elastic, no elastic or zero elastic. It's called no, it's called plastic. Yeah. Plastic, yeah. So this part is called elastic, and then the next part, when it loses its ability, is called plastic. Yeah. See, nobody gets it. So can you write those 2 words down? This one, before the elastic limit, this part is called elastic. Then after the elastic limit, this part is called plastic, with a P. P-L-A-S-T-I-C. Plastic and elastic. I think because in English, when we describe a material as plastic, we describe it as almost being like squishy, that you can squeeze it and it keeps its shape. You know, like you know that the stuff the kids play with, the Play-Doh. We would actually describe that as plastic, because when you squish it, it doesn't restore to its original shape. So in English, to describe a material as plastic is to describe it as to keep its shape. to not have the ability to return to its natural shape. So as you were saying, Monica, there, a material won't follow Hooke's law for any x. It only follows it up to a point. That point is called the elastic limit. Okay. Continue? Yeah. So some more terms, I'm afraid. Elastic. The material follows Hooke's law. You know this already. It's the straight line part of the graph. And plastic. The material no longer follows Hooke's law. It's the curved part of the graph. Elastic limit. The point the material is no longer elastic and becomes plastic. But if you understand that and you wrote that on your graph and you have that as an idea, that's okay. You don't need to write these down. I just want to make sure you're clear on the meaning. So let's just check here. Let's see, what material could we have? Like, elastic or plastic? Plastic, because if I fold it over hard enough, it won't fold back to its original shape. What else? Like my scarf, yes, it's kind of elastic because it can stretch back, but really maybe we can call it more plastic because it holds its shape, you know. What about the can?
Plastic.
Yeah, again, like it can be, if he just squeezes it a little bit, it's kind of elastic. That's the elastic part. But if you hold it too much, then it reaches the elastic limit and then becomes plastic. It won't return to its shape. Yep. Okay, we're happy with those terms? Yes? Okay. Now, a mass M is hung to an elastic material which hangs from the ceiling, or the mass sits on top of the spring. In both cases, the situation is the same. A mass at the end of a material obeys Hooke's law. What equation can be found for such a motion? Let's look at the first case, although the formula works for both. Now, I usually do the proof of this formula. Will I do it this year? Well, the proof's not on the exam.
No.
Well, I'll give you the story anyway. So what happens here is this is hanging from the ceiling, and there's two forces here, mg and the upward force, which is the tension. But because this is a spring, that tension will equal kx, where x is the extension. So perhaps at the beginning of the story it was like this, and then somebody comes along with a mass m and attaches it to the end, and then it extends the distance x. So now it's in equilibrium, it's at rest. What would happen if somebody came along and pulled this down a little bit? What would happen if they let go now? Thank you for the sound effect. It would go flying back up and down like this. In fact, this is what type of motion? Yes? Yeah, where this is the amplitude. Okay? There is a formula which I normally prove. A bit like the formula for the pendulum. I gave you the proof for that formula. I could give you the proof here, but there's not a lot of need for the proof. The reason I gave you the proof for the pendulum formula is because you'll do a lab experiment on the pendulum formula, and you should include the proof in your notes. There is no lab experiment that will be done on this, and there's no requirement for the exam to know the proof. If you really want to see the proof, I can do it in the tutorial next week. But for today, I'll just give you the result of this situation. The formula is for the periodic time is equal to, and it even looks a bit like the formula for the pendulum, 2 pi, but instead of an L, it's not an L, it's an M, and instead of a G, in the case of the spring here, it's a K. So it's actually nearly the same formula, because if you think about it, what is the key property for the pendulum? It's its length, which is like the M on the top. And also, what is the key property of the environment for the pendulum? It's the G, because the G can be different in different planets. What is the key property of the environment for this experiment? It's the spring constant, how stiff it is, the K. So you can actually see a parallel story with the pendulum in this. But what's really nice about this formula is this formula works if the spring is like this, or if it's like this horizontally. Now that might come as a surprise, because you might be saying, how could this be the same? Because in this story here, we have gravity, and in this story here, no gravity. And this is still the same formula if this is out in space. Now you might be thinking, why is that true? Well, because if you look at the formula, there is no G in it. So the G could be 9.81, the G could be 0, the G could be 0 if it's on the ground, the G could be 100. It doesn't affect the time. And this might surprise you, because you think, wait, if the G is really big, doesn't that make the mass here, the weight, really big? So shouldn't it be a different time? It's not. And another thing which you notice, this formula has no amplitude in it. This means if I pull it down a little bit and let go, or if I pull it down a lot and let go, the time is the same. Again, think about the pendulum. We had a similar situation with the pendulum. If I pull it out a little or more, it's the same time. What if I make the mass heavier? The time is the same. Yeah, because it's 2 pi root L over G. There's no mass in it. Now, the mass does matter here though. It does matter. If you increase the mass, what happens to the time? It increases. And if you increase the K, if you make the spring stronger, what happens to the time? Yeah, decreases. Okay, so this formula, please notice, an important formula for this, and it's useful because of its ability to work in different directions. Got this? Yeah? Okay. Got this formula? Hang in there, Jerry. Be strong. Continue? Okay. Right. That's the formula. 2 pi root M over K. Note the absence of A and the natural length as well. And also I should have said the absence of G. There's no G here. Okay, let's have a look at our first example. Some kind of rubber band has a natural length of 10 centimeters and a spring constant of 1. The rubber band is stretched to twice its length. How much force do you need to do this? Okay, I think you can do this. I've only given you 3 formulas, so you need the first formula from Hooke's law. Tell me what the force required here is. 0.1 newtons, yeah. Because it's 0.1 times 1. That's it. So it's an easy example to start with. Continue. Okay. A spring is hanging from the ceiling. A weight of 2 kilograms is put at the end of the spring, and the spring extends 5 centimeters. What is the constant? Okay, let me draw this story for you here. What you have is a spring, and then you hang a mass at the end of it of 2 kilograms, and the result is it causes an extension of 5 centimeters. What's the K is my question. Alright, what's the force here? Yeah, and what's the force here? Kx, which is 0.05 K. Yeah? So, this should equal this. Putting that together, we get K is 2G over 0.05. When you're ready, please. 392.4 newtons per meter. Got that? KJ? Yep. Okay. A spring with spring constant of 2 is attached to the wall. A boy pulls it out a distance of 10 centimeters. How much work was done by the boy? So in this story here, you have a wall, you have a spring, and then the boy comes along and pulls it out a distance of, it extends out a distance of 10 centimeters. And the K here is 2 newtons per meter. How much work did he do? Well, we have the formula. The work that he did was given the spring potential energy, which is a half kx squared, which is a half times 2 times 0.1 squared, which is 0.01 joules, which is 10 millijoules. Is that okay? Continue. Yeah? Okay, next one. A rubber band is attached to the ceiling. A 100 gram weight is hung on the rubber band and it extends 5 centimeters. The weight is pulled down a further 4 centimeters and released. How long until the weight reaches its maximum height? Okay, so let me draw this one for you. Here's the ceiling. Here's the rubber band. Then, next part of the story, you hang a weight at the end of it, 0.1 kilograms, and this causes it to extend by 5 centimeters. Then somebody comes along and pulls it down a further 4 centimeters, yeah. So this distance here is 4 centimeters. And they release it and it's going to snap back up and down like this. And my question is, how long until it's back here? Yeah? Okay, let's look at each picture. In this picture, I've got nothing. But in this picture, I know that the force here is equal to the force here. So I know 0.1 G equals K 0.05. So then I get my K is, what's it, 392? What's the K here? It's 196.2. What is it? 19.62 newtons per meter. Yeah. Now, in this picture, what type of motion is this? Simple harmonic motion. And you have a formula for the time. The time equals 2 pi root m over k. So, what's the time here?
0.449.
Yeah. So my final answer is the time I want will be half of this. Because I only wanted to go half a circle, or half a cycle. Because that t is the time for it to go up and down. So the answer will be 0.225 seconds. In fact, I didn't need to tell you the 4 centimeters. How long until it's reached its maximum height? Yes? What are you going to ask me?
No, I'm asking how can I know to multiply by the half in which situation?
It's because I was looking for the time, not for one period, but the time to reach the maximum. How long until the weight reaches its... maximum height. Yeah, no, that's right. Sorry, I said length. How long until the weight reaches its maximum height? So, the t is a full cycle. The answer is going to be half a t. Yeah? Continue? I think that was the last one. Yes, it was. Okay, let me have a look here. Wonderful. I'll let you try these for 5 minutes, then you can take a break after 5 minutes. Question 1 and 2 and 3, 4, yeah, they're all okay. I'm very happy with question 5. Very happy. I think you'll like it when you see it. No, I'm taking the credit for this one. Look at it. I'll upload the answers when I make them.
Thank you.
Did you see that I uploaded the answers to YouTube for the other lessons?
Well, one is missing.
Which one's missing?
That's the point I knew about.
Okay, I'll check maybe. No, I'll check.
Either of that. Yeah. One is missing.
One of them's missing. Okay, I'll check. Right, try these for 5 minutes, please.